previous video session we have finished exercise 2.2. In exercise 2.2 we have saw addition of two complex numbers and multiplication of complex numbers also, and complex numbers pointing in the organ plane. The few sums we have saw in exercise 2.2. Now we are going to move towards exercise 2.3. In exercise 2.3, first we are going to see basic algebraic properties of complex numbers. Basic algebraic properties of complex numbers. So the first property is nothing but closure property. The first property is closure property. In this left hand side table, this is addition. The complex numbers satisfy the following properties under addition. This is called properties under addition. This property is under multiplication. Multiplication. Left hand side property fully under addition. Right hand side property is fully multiplication. The first property is closure property. Both sides we have closure property. Addition we have a closure property, and multiplication we have closure property. The first property is nothing but adding two complex numbers once again gives us a complex numbers. That's all. Addition in under the addition, no, adding two complex numbers. For any two complex numbers z1 z2, the sum z1 z2 z1 plus z2 is also a complex numbers. If we are going to add any two complex number, once again a complex number. The same. If we are going to multiply any two complex number, it's also once again a complex number. It is under addition, it is under multiplication. This is a closure property. Adding two complex numbers is once again a complex number. Multiplying two complex number is once again a complex number. Therefore, both the things closure property satisfies. Adding of two complex numbers is once again a complex number. We don't need to worry. Multiplication two complex numbers is also a complex number. We don't need to worry. So only closure property satisfies. So second property under addition and multiplication is commutative property. Then commutative property nothing but a plus b is equal to b plus a. A into b is equal to b into a. This is a commutative property. The same for any two complex numbers z1 plus z2, nothing but z1 plus z2 is equal to z2 plus z1. Therefore, z1 plus z2 is equal to z2 plus z1. That's all. The same for any two complex numbers z1 z2, z1 z2 is equal to z2 z1. The same as we done in algebraic expressions. z1 plus z2 is equal to z2 plus z1, z1 z2 is equal to z2 and z1. This is a commutative property will satisfy. Commutative property will satisfy under addition and under multiplication. Left hand side is addition, right hand side is multiplication. Next, associative property, z1 plus z2 plus z3 is equal to z1 plus z2 plus z3. Here bracket comes here, bracket comes here. So in associative property under multiplication, z1 into z2 into z3 is equal to z1 into z2 into z3. This is a property, associative property under addition, associative property under multiplication. So only addition is present, multiplication is present. The last property is additive identity. The identity is nothing but, for example, 1 plus dash gives 1, nothing but 0. That's all. If you are going to put 0, 1 plus 0 gives only 0. For example, a plus dash gives a. What do you want to add? 0. A plus 0 only a. Therefore, a is the additive identity. A is the additive identity. Adding of one number which gives the same number. Adding of any number which gives the same number. So what we get, we need to add 0 only. So the same, see, one complex numbers plus 0, 0 plus complex numbers, once again a complex number. Therefore, there exists a complex number 0 such that for every complex number z, z plus 0 is equal to 0 plus z equals 0. See here, for multiply, this is on addition, no. 1 plus 0 is equal to, if multiply 1 into dash is equal to 1, nothing but 1. For example, a into dash is equal to a into 1 into 1. Wait, same. If suppose we are going to use a or we can use b, I need to get 1. So what I want to get, I need to put 1 only. A into 1 is equal to a. B into 1 is equal to b. B into 1 is equal to b. So 1 is the multiplicative identity. I want to say one thing. Always addition, for addition, additive identity will be 0. For multiplication, multiplicative identity is always 1. It's always 1. Somewhat differs, but in this we no problem. Additive identity is always 0 for addition. Multiplicative identity is always 1 in multiplication. Next step, find last is additive inverse. The additive inverse is nothing but we need to put get 0 because the 0 we need to get 0 here 0. So a plus dash gives 0, nothing but minus a plus minus a, this 0 comes here, the same 1 multiplier comes here, a into dash gives 1, nothing but 1 by a, that's all. This is called multiplicity inverse. I will tell you once again, additive identity is 0, we need to give right answer 0. For example, f into minus f, f plus minus f, which gives us 0. The same way also multiple identity is 1, so put 1 here. If I going to put f into 1 by f gets cancelled, answer is 1. So it is called multiplicity inverse, multiplicative inverse. Last distributive property, multiplication distribute is over addition. Distributive property under addition, z1 open the bracket, z2 plus z3 gives z1 z2, z1 into z2 plus z1 into z3. Another one also, z1 z2 into z3 is nothing but z1 z3 plus z2 z3. This is a distributive property under addition. So next, this is a proof for commutative property under addition. Another proof, inverse property for multiplication. Read these two proof is given as back sign. Property 1, commutative property and addition is a very easy proof. Inverse property of multiplication, this also very easiest to prove. You can learn this proof very easily. So after doing this, sum of the identity is nothing but z power m, z power n is nothing but z power m plus n. If z is common, I add power m plus n. Z power m divided by z power n, we can write z power m minus n. Z power m whole power n is nothing but z power multiply m into n. Z1 Z2 whole power m, we can separate the powers, Z1 whole power m and Z2 whole power m. So within this we are finishing this introduction and we start our exercise 2.3. Exercise 2.3, first sum. Z1 is 1 minus 3i, Z2 is minus 4i and Z3 is equal to 5. To show that Z1 plus Z2 plus Z3 is equal to Z1 plus Z2 plus Z3. Z1 into Z2 into Z3 is equal to Z1 Z2 into Z3. This is nothing but associative property under addition. This is associative property under multiplication. Both are associative properties I need to prove. Therefore, proof of subdivision 1. Taking first LHS. LHS of first subdivision 1 is nothing but Z1 plus Z2 plus Z3. First we know we need to add bracket first. Z1 plus Z2. Z1 value is 1 minus 3i plus Z2 value is minus 4i. So we know how to add real and real, imaginary. So 1 minus 3a minus 4a, which gives us minus 7i. 1 minus 3a minus 4a is minus 7i. Now we need to add this one and this one. Z1 plus Z2 finally plus Z3 is equal to Z1 plus Z2 is 1 minus 7i plus Z3 answer is 5. So real and real, 1 plus 5 is 6. There is no imaginary, to write as it is. 6 minus 7i. So keep it as equation 1. 6 minus 7i, keep it as equation 1. The final LHS we have finished. Next RHS. RHS of subdivision 1. RHS of subdivision 1 is Z1 plus Z2 plus Z3. First you want to find the bracket. Z2 plus Z3. Z2 is minus 4i plus Z3 is 5. Z2, this is Z2 plus Z3. Now we need to add all the things. So Z1 plus Z2 plus Z3 is equal to, Z1 answer is 1 minus 3i plus Z2 plus Z3 is minus 4i, so written in bracket, plus 5 is equal to 1 and 5 is real, so 6 minus 3i minus 4i, which gives minus 7i. Keep it as equation 2. So from equation 1 and 2, Z1 plus Z2 plus Z3 is equal to Z1 plus Z2 plus Z3. Hence proved. hence proved. So this is associative property under addition. That is second subdivision, associative property under multiplication. Proof of subdivision 2. Proof of subdivision 2. LHS of subdivision 2 is nothing but Z1 Z2 into Z3. First we need to find the bracket. Z1 into Z2 is equal to, Z1 is 1 minus 3i into Z2 is minus 4i. Now we can start our multiplication. 1 into minus 4i, which gives minus 4i, minus into minus plus, 3 4s are 12, I into I square is minus 1. So final answer is minus plus into minus minus 12 and minus 4i. Now we need to multiply with Z3. Z1 Z2 is multiplied with Z3. What is Z1 Z2 answer? Minus 12 minus 4i. Z3 answer is 5. So minus 12 into 5 is minus 60, minus 4 5s are 28. Minus 60 and minus 28. Keep it as equation 1. Now RHS of subdivision 2 is Z1 bracket Z2 and Z3. First we need to find the bracket only. So find Z2 and Z3. Z2 is minus 4i and Z3 is 5. So answer is minus 4 5s are 20i. So finally I need to write fully. Z1, open the bracket, Z2 and Z3 is equal to, Z1 answer is 1 minus 3i into minus 20i. So 1 into minus 20 is minus 20i, minus into minus plus 3 2 20s are 60, I into I square is minus 1. So plus into minus minus 60 minus 28. Keep it as equation 2. Therefore from equation 1 and 2, Z1 into Z2 into Z3 is equal to Z1 into Z2 into Z3. Hence proved. The first sum, 2 subdivision is over. Next we will move towards the second sum. Second sum, Z1 is equal to 3, Z2 is equal to minus 7i, Z3 is equal to 5 plus 4i. To show Z1 into Z2 plus Z3 is equal to Z1 Z2 plus Z1 Z3. Z1 plus Z2 into Z3 is nothing but Z1 Z3 plus Z2 into Z3. So this is distributive property under addition. So we will move towards the sum. So how I can move? So proof of subdivision 1. In previous sum we have saw associative property of addition, associative property of multiplication. Distributive property, it contains multiplication and addition, multiplication over addition. Both are distributive property, multiplication over addition. So we do proof of subdivision 1. First we will see LHS of subdivision 1. Z1 Z2 plus Z3 is equal to, not is equal to, this is LHS. First we need to write the bracket Z2 plus Z3. What is Z2? Minus 7i. Z3 is 5 plus 4i. We know real is 5 alone. Imagine is minus 7 plus 4, which gives us 5 minus 3i. So we need to do Z1 into Z2 plus Z3. Z1 answer is 3. Z2 plus Z3 answer is 5 minus 3i. 5 minus 3i. So final answer is going to be 3 5s are 15. 3 3s are 9i. So 15 minus 9i. Keep it as equation 1. So second subdivision, no, first is RHS of subdivision 1. RHS of subdivision 1, Z1 into Z2. First I need to multiply Z1 into Z2. Z1 is 3, Z2 is minus 7i. So 3 7s are 21, minus 21i. Minus 21i. I will erase and write minus 21i. Next, z1 into z3. z1 into z3. What is z1 z3? z1 is nothing but 3. z3 is 5 plus 4i. So we need to multiply. 3 5s are 15. 3 4s are 12i. Now we need to add this. z1 into z2 plus z1 into z3. z1 into z2 is minus 21i plus z1 z3 is 15 plus 12i. So this 15 minus 21i plus 12i, which gives us minus 9i. Keep it as equation 2. From equation 1 and 2, distributive law, multiplication over addition. This is nothing but z1 z2 plus z3 is equal to z1 into z2 plus z1 into z3. Hence proved. Next, second subdivision. So LHS of subdivision 2, z1 plus z2 into z3. First we need to take the bracket. z1 plus z2. z1 is 3, z2 is minus 7i. So leave it as it is. z1 plus z2. Then I need to multiply z3. z1 plus z2 is multiplied with z3. z1 plus z2 is 3 minus 7i. z3 is 5 plus 4i. I need to multiply this one. 3 5s are 15. Just like a algebraic multiplication. 3 4s are 12i minus 7 5s are 35i. Minus into plus minus. 7 4s are 28. I into I square. I square is minus 1. So 15 minus into minus plus 28. 15 plus 28 gives 43. Minus 35 plus 12i, which gives minus 23i. Keep it as equation 1. Next, RHS of subdivision 2. RHS of subdivision 2 is z1 into z3 plus z2 into z3. So first write z1 into z3. z1 is 3 and z3 is 5 plus 4i. You can multiply. 3 5s are 15, 3 4s are 12i. Next, z2 into z3. z2 is minus 7i. z3 is 5 plus 4i. Now we can start a multiplication. 7 5s are minus 35i. Minus into plus minus. 7 4s are 28. I into I square. I square is minus 1. So minus 35i plus 28. Now we need to add both this expression. z1 into z3 plus z2 into z3 is equal to 15 plus 12i minus 35i plus 28. The same here, 15 and plus 28. 12 minus 35. The same answer is 43 minus 23i. Keep it as equation 2. From equation 1 and 2, z1 plus z2 into z3 is equal to z1 into z3 plus z2 into z3. Hence proved. z1 is equal to 2 plus 5i. z2 is equal to minus 3 minus 4i. z3 is equal to 1 plus i. Find the additive. Find the additive and multiplicative inverse of z1, z2 and z3. To find this answer very easily, to solve this sum very easily, I am going to teach you one formula. For example, additive inverse of a. Additive inverse of a is nothing but minus a. That's all. Suppose additive inverse of z is nothing but minus z. Plus z means minus z. That's all. The same for multiplication also. Multiplicative inverse. Multiplicative inverse of a is 1 by a. The same. Multiplicative inverse of z is 1 by z. That's all. Because the main thing is a minus a, which gives answer as 0. Z minus z, which gives answer as 0. Here a into 1 by a. This is addition, no, but we addition only, but here put plus, no problem. Here a into 1 by a, answer is 1. Z into 1 by z is answer is 1. So only, because we saw in the properties 0 should come here and 1 should come here. So additive inverse is for a is minus a. Additive inverse of z is minus. These are some examples. Multiplicative inverse of a is 1 by a. Multiplicative inverse of z is 1 by z. See, first we have seen, first we will find the additive inverse. Additive inverse. Additive inverse. Additive inverse of z1, z2 and z3. Additive inverse of z1. Additive inverse z1 is nothing but 2 plus pi I. Additive inverse of z1. Additive inverse of z1 is, we will put is here. How? Additive inverse of z1 is minus z1. Additive inverse z2 is minus z2. Additive inverse z3 is minus z3. Nothing but I need to put minus z1. So minus 2 minus 5i. Z1 is 2 plus 5i. Minus z1 is minus 2 minus 5i. Minus z2. This plus z2. When minus z2. So this minus become plus. This plus become, this minus become plus. 3 plus 4i. 3 plus 4i. Finally 1 plus I, which becomes minus 1 minus I. Very easily we can solve this sum. You don't need to confuse of yourself. You don't need to confuse of yourself. You can easily solve this sum. For example, see, a is 1 plus I. What will minus a? Minus 1 minus I. That's all. A is 1 plus I. Minus a minus I. A. Additive inverse of a is minus a. 1 plus I is nothing but minus 1 minus I. The same. Additive inverse of z1, z2 and z3 is minus z1, minus z2 and minus z3. So minus z1 is minus 2 minus 5i. Minus z2 is plus 3 plus 4i. Minus z3 is minus 1 minus I. This is additive inverse of z2 and z3. Next we are going to find multiplicative inverse. You know, multiplicative inverse of z1 is 1 by z1. Nothing but 1 divided by, what is z1? Z1 is nothing but 2 plus 5i. I have already told you should not present in the denominator. Always the complex one should present in the numerator, is the correct form. So you need to conjugate 2 plus 5i. Now conjugate is nothing but this plus I, this plus I, no, connect to minus I. 2 minus 5i divided by 2 minus 5i. Very simple process. This plus I, this is plus I. Suppose minus I means plus I, plus 5i plus 5i. So how we can write? See, 1 into 2 minus 5 is nothing but 2 minus 5i divided by, this is a plus b, a minus b. Formula is a square minus b square. 2 square minus 5i the whole square. 2 minus 5i divided by 2 square is 4 minus 5 square is 25, I square is minus 1. So answer is going to be 2 minus 5i divided by 4 plus 25. Answer is 4 plus 25 is 29. 1 divided by 29, 2 minus 5i. 1 divided by 29, 2 minus 5i. Otherwise we can write 2 by 29 minus 5i by 29. This is also correct answer. This is also correct answer. This is multiplicative z1. Why we are conjugating? Because denominator should not present the complex number. Always numerator should present. So we are conjugate. Plus 5i, I am going to minus 5i minus 5i. A plus b, a minus b formula, a square minus b square. 2 square, a square minus b square, no. A square minus b square is 5i, no. 5i the whole square. So next, multiplicative inverse of z2. Multiplicative z2 is 1 by z2. That's all. So 1 divided by z2 value is minus 3 minus 4i. You should not present a denominator. So 1 divided by minus 3 minus 4i conjugate. Minus 3, this minus 4i, I need to change plus 4i minus 3 plus 4i. I need to change one in the minus 4i, nothing but plus 4i plus 4i. So 1 into minus 3 plus minus 3 plus 4i. The same formula, a minus b, a plus b. Formula is a square minus b square. The same formula I can use here. Minus 3 the whole square, a square minus b square. What is b square? 4i the whole square. So minus 3 plus 4i divided by minus 3 square is 9 minus 4 square. 4 square is 16 I square is minus 1 minus 3 plus 4i divided by minus into minus plus 16. 9 plus 16 is 25. You can write this answer. Otherwise 1 by 25 into minus 3 plus 4i, or else or minus 3 by 25 plus 4i by 25. This also correct. Finally, the last one, multiplicative inverse of Z3 is 1 by Z3 is equal to 1 by, what is Z3 value? 1 plus I. Z3 value is 1 by 1 plus I. Now I want to conjugate. Why? The complex number should not present a denominator. 1 divided by 1 plus I is nothing but, this is plus I, no? So 1 minus I divided by 1 minus I. So 1 into 1 minus I is 1 minus I. A plus B, A minus B, A square minus B square is nothing. B is also 1 only. Coefficient of I is nothing but 1. This also 1 only. I square, I the whole square. 1 A plus B, A minus B, A square minus B square is I, no? I the whole square. So 1 minus I divided by 1 square is 1 minus I square is minus 1. So 1 minus I minus into minus plus 1 plus 1, which gives us 2. How we can write 1 divided by 2, open the bracket, 1 minus I. 1 minus I divided by 1 by 2. Otherwise 1 by 2 minus I by 2. This is also correct answer. So within this we are finishing exercise 2.3.